Hey everybody, welcome back to another one of Dr. Cool Cat's sessions. I'm so glad you're here. Today, we're going to tackle a topic that, let's be honest, trips up a ton of people on the GED Science test, and that's experimental data. If you've ever had that moment where your brain just freezes up looking at charts and numbers, well, this explainer is for you. Let's dive in.
So, let me ask you this, and be honest. When you're flipping through the test and you land on a question that's just packed with tables, decimal points, lab results, does your heart start beating a little faster? You know that feeling, that little voice that says, maybe I should just guess and move on.
Well, if you said yes, I promise you, you are not alone. That is a super common feeling. But here's the secret. Reading this data isn't some magic power you're either born with or you're not. It is absolutely a skill. And today, we're going to build that skill step by step and turn those scary-looking questions into points in your pocket.
Okay, first things first, we've got to totally rewire our brains about one little word, error. See, in day-to-day life, an error is a mistake, right? Something you did wrong. But in science, nope, it's something else entirely, and getting this is the absolute first key to unlocking these questions. You have to get this straight. Scientific error is not about messing up, it's not about being wrong, it's about being a realist. The simple fact is, no measurement in the real world is ever 100% perfect. There are always going to be these tiny, tiny little variations and uncertainties. Good science doesn't try to hide that. It actually measures it.
So this error thing basically comes in two main flavors. Over on the left, we've got random error. I like to call this noise. Think of it like tiny, unpredictable little wiggles in your data. Maybe you're timing something with a stopwatch, and one time you're a fraction of a second early, the next time you're a fraction of a second late. So how do you fix it? Easy. You just do it a bunch of times and take the average. Those little wiggles will cancel each other out. Now, on the right, we have systematic error. This is bias, and it's a bigger deal. It's a consistent push, always in the same direction, like a scale that's busted and always reads 0.4 grams too heavy. Taking an average won't help you here. You have to actually fix or calibrate the equipment itself.
Okay, so now we get what error is, but how in the world do you actually use that on test day when you're looking at a question? Well, we've got a secret weapon for you, a kind of mental checklist you can use every single time.
And here it is. Your toolkit is the acronym MEASURE. Think of it as a checklist that makes sure you've covered all your bases on a data problem. We're going to touch on all of these, but you know what? Today, we're really going to zone in on those last few letters, calculating uncertainty, reasoning about error, and using evidence for your claim, because that's where the real high-value points are hidden. Now let's just do a super quick look at the S, significant figures. Don't let all the rules you might have learned in a chemistry class freak you out. For the GED, you really just need the basics. Here's the deal. When you multiply or divide, your answer can only be as precise as your least precise measurement. So you just keep the fewest number of sig figs. And when you add or subtract, it's even simpler. It's all about the decimal places. Just match the number with the fewest places after the decimal. That's really it.
All right, let's start putting this stuff into practice. We're going to focus on that U for uncertainty in our measure toolkit. And on the GED, that often boils down to being able to crunch two key percentages.
First up, we've got percent error. This is the formula you're going to use when the problem gives you a known or accepted value, like a scientific fact. The goal is super simple. How far off was your measurement from the real thing? You just find the difference between what you measured and the accepted value, divide it by that accepted value, and then times it by 100.
So let's make this real. Imagine the known density of some metal is 2.70 grams per cubic centimeter. That's the fact. But in your experiment, you measured it and got 2.58. So we're just going to plug those numbers right into the formula?
And boom, you get 4.44%. See, that number isn't just a number. It tells a story. It tells us that our experiment was off from the known value by just under 4.5%.
Okay, but what if there isn't a true value? What if you're just comparing two groups from your own experiment? Maybe a group that got a treatment versus a group that didn't. Well, for that, you use percent difference. You're comparing your result A to your result B. And pay close attention to the bottom of that fraction. You're dividing by the average of the two, not just one of them. That's a key difference.
Let's look at another example. Say you're studying plant growth. Group A, your control group, grew to an average of 18.2 centimeters. But Group B, which got a new fertilizer, grew to 20.6 centimeters. So let's run these numbers through that percent difference formula.
And what you get is a difference of about 12.4%. This is so much more powerful than just saying Group B was taller. Now you can say how much taller with a precise number to back it up. Group B was taller by 12.4%.
And now, we get to the most important part of all. I mean, crunching numbers is one thing, but what the GED really wants to know is, can you turn those numbers into a solid, valid, scientific claim? This is all about learning to respect the uncertainty in your data.
Okay, take a look at this bar chart. It's showing the average dissolved oxygen in two different lakes. Now, at first glance, you see Lake B's bar is higher than Lake A's, right? Simple. But wait, look closer. See those little black lines on top of the bars? Those are error bars. They show us the range of uncertainty for each measurement. And do you see what's happening? The range for Lake A and the range for Lake B, they overlap.
And that overlap is everything. It means you cannot just say, Lake B has more oxygen. A scientist would never say that. The best, most accurate claim you can make is a cautious one. Because those error bars overlap, the data suggests that even though B's average looks higher, we can't be sure the difference is real or if it's just due to random chance. Using that kind of careful language is going to score you big points.
Oh, and here's a little cheat sheet for you. If you ever get one of those questions that asks, how could this experiment be better? These are your golden answers right here. Do more trials to reduce that random noise. Calibrate your equipment to get rid of systematic bias. And make sure you're controlling all the other variables so you know you're only testing the one thing you care about.
All right, you've seen the concepts, you've seen the formulas, we've walked through it together. Now, it's your turn. Time for you to put on the lab coat and be the scientist.
Here is your challenge problem. You're comparing two fertilizers. One group of plants grew to a mean height of 22.8 centimeters. The other group grew to 24.1 centimeters. Your job is to calculate the percent difference. So I want you to go ahead and pause this explainer right now. Grab a calculator or a piece of paper and actually solve it. I'll wait.
Okay, you got an answer? Let's walk through it together and see how you did. So first, you find the difference between the two numbers, which is 1.3. Then you find the average of the two, which comes out to 23.45. Next up, you divide that difference by the average, and the very last step is to multiply by 100 to make it a percent.
Which gives us a final answer of 5.5%, rounded to two significant figures. Awesome work!
So, how'd you do? If you got 5.5%, seriously, congratulations. That's fantastic. If you didn't, hey, that's exactly what practice is for. Do me a favor, drop a comment below and let us know what you got, or what the trickiest step was for you. Was it remembering to divide by the average, or maybe the final rounding? Sharing that stuff really helps everybody learn. You all did some fantastic work today. If this helped you make sense of all this data stuff, do us a huge favor and hit that like button. And definitely subscribe for more GED help from the whole Dr. Cool Cat team. We'll see you in the next one.